we'd originally learned about alkanes, and then we learned about alkenes. And one of the things we learned about alkenes is that they're more reactive than alkanes. You can add things across the double bond. And we learned about Markovnikov and how he showed that when you hydrate a double bond, where the hydroxyl group goes and where the other hydrogen goes. But one of the things we haven't really focused on is why alkenes are more reactive than alkanes. And one of the reasons is if you can polarize a bond, you can make it much more amenable to attack by another atom or another molecule. If you have a non-polar molecule with non-polar bonds, basically there's no difference. As we know, that's the definition of non-polar. So you have an equal distribution of electron density around that bond. And so it's really difficult to try and push or pull it in one direction or another. When you have a double bond, now you have twice the number of electrons between those carbon atoms. And it makes it easier to polarize it, to push the electron density towards one of the carbons and away from the other one. And when you do that, you create a dipole. And dipoles, we know, attract electrons. Like we know with hydrogen bonding, if you have a dipole, a really strong dipole, like the oxygen-hydrogen one, it attracts the attention of other electron-rich regions that then bond with the hydrogen. And the same is true with organic molecules. And so we're going to learn that once you start introducing other atoms, and we call them heteroatoms because they're not carbon and they're not hydrogen, like oxygen, sulfur, and nitrogen, we're going to learn about this time. Once you start introducing those other atoms, they change the chemistry of those carbon-carbon bonds. And you can start breaking them. You can start adding things to them. You can start doing a lot more reactions than you could when you just had carbon-hydrogen or carbon-carbon bonds. So what we're really going to get into is learning about what we call functional groups. Now, functional groups are what they sort of sound like. They have functions. They have what we say is chemical reactivity. And they have unique chemical reactivity that is the same for each functional group. So organic compounds can have oxygen and nitrogen and sulfur and phosphorus and all these other atoms in them. They're still mostly carbon, but they can contain all this other stuff too. And those are called heteroatoms. And a group of atoms, a group of these heteroatoms plus carbon bonded in a specific way, we call that a functional group. And all functional groups are similar to each other. They have similar chemical properties. And so organic compounds with the same functional group sort of react all the same way. So what are some of these functional groups? Most functional groups contain the three most common heteroatoms, which are the ones we're going to be learning about tonight: oxygen, nitrogen, and sulfur. And one of the most common functional group, let me clear these out. One of the most common functional groups is called a carbonyl. Carbonyl just means a carbon double bonded to an oxygen. We're familiar with that. We just haven't called it a carbonyl group before. And why the carbonyl group is so functional and essential to organic chemistry is because it creates that dipole I was talking about. Because we know oxygen is much more electronegative than carbon. And so when carbon is bonded to oxygen, and especially when it's double bonded, it creates a very large partial positive charge on the carbon and a partial negative charge on the oxygen. When you have a single bond, remember, that's just 2 electrons being shared with oxygen. But when you have a double bond, that's 4 electrons being shared with oxygen, and oxygen's keeping all 4 of them close to itself. That increases the partial positive charge on that carbon and causes other atoms with negative charges or just with large electron clouds to be attracted to that carbon and undergo chemical reactions. And so one of the functional groups that contains a carbonyl is called a carboxylic acid. And what carboxylic acid have we actually used in lab so far? We've actually used one of those in a lab a couple times, actually. At least 3 so far.
Is it the acetic acid?
Acetic acid, right. Acetic acid is the second most simple carboxylic acid. Acetic acid is just this group, that's a carboxylic acid group, with a methyl group attached. The simplest carboxylic acid would just have a hydrogen there, and that's called formic acid. Formic acid is actually produced by those stinging ants in Texas that everyone's scared of, those red ants actually spray formic acid on you. It's kind of nasty. So we've used acetic acid in lab. And this carboxylic acid, why it's so acidic is because this carbon has such a high partial positive charge, and it's attached to 2 oxygens. So that means that this particular oxygen is even more negative than usual because of the partial positive charge is higher on that carbon. That increases the partial negative charge in that oxygen and makes it freer to steal both of those electrons from its bond with hydrogen and then just release it as a proton. But we know it doesn't do a great job at that. It's not a strong acid. We know it with acetic acid, it only does it about 2 out of every 1,000 molecules or so. So it's not real great at doing it. But without this carbonyl group, it really wouldn't do it at all. And so it's the carbonyl group, and we call it an electron withdrawing group because it is pulling electrons away from that carbon. That's what an electron withdrawing group does. And so without that, it would hardly be acidic at all. It would just be an alcohol. Okay. Now we talk about functional groups, and we can say that each of these molecules has the same functional group. So this is acetic acid. This is palmitic acid. The only difference between them is that palmitic acid has a really long hydrophobic tail with a very long, what we call fatty acid tail with lots and lots and lots of carbons in it. But the functional group is the same. And so when we're talking about organic compounds, the functional group is the reactive part. And what do we call the rest of it? Well, we call the rest of it R, which really imaginatively stands for rest of molecule. So this is what we would call a sort of representative structure of a carboxylic acid, just R with the carboxylic acid group on it. And we do that a lot. R just represents anything, usually a carbon-carbon chain, or sometimes it's a benzene ring or something else. But generally it refers to the non-reactive part of the molecule. So as it says down here at the bottom, can represent anything from 1 carbon to 100 carbons to 12 to a ring to basically anything that isn't the reactive part of the molecule. So here's some of the basic functional groups that we'll be looking at. Notice that alkane does not have a functional group because they are not reactive. Basically, the only reaction you see alkanes involved in is combustion. So basically everything combusts if you heat it high enough. So it's not terribly reactive molecule. Alkenes, we learned, are reactive, and that makes this a functional group. And so with the suffix -ene at the end. Alkyne is the triple bond. That's even more reactive than the double bond because now you have 6 electrons being shared between those 2 carbons. And the more electrons you have, the easier it is to polarize it. And we sort of learned that when we were dealing with London dispersion force, if you remember. The larger the molecule, the greater the London dispersion force. So fluorine didn't have much of a London dispersion force because it's a really small atom that holds on to its electrons very tightly. Iodine, on the other hand, has a great big electron cloud and is really easy to polarize. And so that's why F2 is a gas and I2 is a solid, just because you can polarize that electron cloud much more readily. And so we've learned about alcohols a little bit. Alcohol has the functional group OH. We call that a hydroxyl group or an alcohol group, hydroxyl generally. Hydroxyl, there we go. Because basically it comes from hydroxide. So when it's attached to a carbon, we call it hydroxyl. And to show that a molecule is an alcohol, we just put "ol" at the end. We get rid of the ane, and so instead of ethane, we would have ethanol. And now 2 of the groups we're going to be learning about tonight are thiols, which are basically exactly the same as alcohols, but with the substitution of sulfur for oxygen. And we call that a mercaptan. We'll learn a little bit about that, and they smell really bad. That's where the rotten egg smell comes from, is mercaptans. So when you get a sulfur with a hydrogen bonded to it, really bad. And we call those thiols. And they're really, really important for biology. And then ethers is another oxygen-containing molecule. Ether is different from alcohol in that it doesn't have a hydrogen attached to it. It's just oxygen with 2 carbon groups attached on either side. And so we say that it has an R group on one side and generally an R prime group on the other side, if they're different. If it's the same group, we just have ROR. So it's oxygen directly bonded to 2 carbons, and those are called ethers. So 2 other really important groups are aldehydes and ketones. We've already learned a little bit about carboxylic acids so far. It has the carbonyl group with a hydroxyl added. And so when we want to name one of those, we replace the ANE with oic acid, so that acetic acid isn't really the official name of that. We would call it ethanoic acid, but nobody calls it that. We just call it, it's the common name, has been the accepted name for like hundreds of years, so we call it acetic acid, but it's really ethanoic acid. These are called aldehydes. Aldehydes have the carbonyl group, And it's on the terminal end of an alkane or an alkene or whatever. It's on the end, and it has a hydrogen on the end. So the basic functional group is the aldehyde here. It has the carbonyl plus a hydrogen. So it's on the end of the molecule. And aldehydes are very reactive. Yeah, they're super, super reactive because you have this very positive, partial positive charge on the carbon, and you have a hydrogen there, which basically then leaves. And so it's really easy to pull that hydrogen off and then replace it with something else. So aldehydes are super duper reactive. And we were to name them, we just replace the ane at the end with al. Methanal, ethanal, propanal. And you don't have to name, you have to number them because they're always at the end. They're never in the middle because you have a hydrogen on one side of that carbon. When you have two carbons on either side, we call that a ketone. And you're probably familiar with acetone. Acetone is a really good solvent. It basically dissolves everything. It dissolves hydrophilic things like water can. It dissolves hydrophobic things like most organic solvents can. So it's a really good solvent. That's why it's a really good nail polish remover. That's what's in nail polish remover, is acetone. And what it has is a methyl group on one side, double bond in the middle, and a methyl group on the other side. And we just call it acetone. So, and there's any ketone can have basically any two R groups on either side. And when we were naming those, we just name the longest one first, the shorter one second, and then followed by ketone. Or we just give it the number, say where it is, and call it own. So acetone would be 1, 2, 3 carbons. So if it's 3 carbons, what would we call that? What's the root for 3 carbons?
Propane.
Methyl, ethyl, then what?
Propane. Oh, yeah.
Propane. So that would just be propanone. And we wouldn't have to give that a number, because if it's a ketone, it has to be in the middle. So we would just say it's propanone. But it's, again, these common names come up all the time. And so we call that acetone. So it's been called that forever. And then another group that we won't deal with a lot, but I sort of did want to introduce it, is called an ester. So esters are formed, the reaction that forms esters is you take a carboxylic acid like this one and an alcohol like this one, and it's a dehydration reaction. So it removes that hydroxyl group and it removes that hydrogen. So what you get is this group here. So basically, excuse me, you have replaced the hydrogen in the carboxylic group with whatever the non-functional part of the alcohol. And we name those the alcohol first, followed by the acid, and then with 8 at the end. So like this one has methyl alcohol or methanol and the ethyl acid, so ethanoic acid. So we call it methyl because it's the alcohol, and then ethanoate or methyl acetate. So esters are really interesting because if you go on and take an organic chemistry class, and hopefully you will at some point. So if you take a more advanced organic class, you're in a lab, this is definitely an experiment they will have you do, is making esters, and they smell fantastic. They have this really, really great odor. So you can take a carboxylic acid that smells kind of nasty, and an alcohol. We know what alcohol smells like. It doesn't smell great by itself, but you put them together and they make this fantastic smell. And depending which you mix and match, you make, bananas and strawberries and butterscotch and all these wonderful odors. And so they're used a lot in perfumes and food and all different things where you really, really want a nice smell. You will find esters. So these are some of the functional groups with nitrogens. Two basic functional groups we'll be dealing with. One is amines, and you're probably familiar with amines. We've been using one in a lot of our examples. The simplest amine is that one, ammonia. That's the simplest amine there is. Basically just nitrogen attached to 3 different carbons with the lone pair on the nitrogen. But when amines attach themselves to organic compounds, they attach themselves to a carbon. And so we have carbon, and so we have that bonding. And we call that a primary amine, because it's this nitrogen is bonded to 1 carbon. So primary. Same is true with alcohols. So a primary alcohol will be bonded, the carbon that's attached to the ethanol group, or the ethanol group, the hydroxyl group will be attached to only 1 other carbon. Same, so with amines, if the nitrogen is attached to 1 carbon, we call it primary. If it's attached to 2 carbons, we call it secondary. And if it's attached to 3 carbons, we call it tertiary. Tertiary. So this would be a primary. This would also be a primary. You can tell by the number of hydrogens that are there. This one would be secondary because it's attached to 2 different carbons and has only 1 hydrogen bonded to it. And then if you have all 3, then it's a tertiary. Now, the other really important functional group with nitrogen is called an amide. Now, an amide is basically just like an ester. The only difference is we have a carboxylic acid and an amine reacting together. So here's the part that was the carboxylic acid, and then here's the part with the amine. And so same rule sort of applies as with the amines. A primary would have just a single carbon, secondary would have 2, and a tertiary would have 3. Now, why amide groups are so important is that these are the groups that keep your proteins together. Because what 2 functional groups do you think an amino acid has? We know that amino acids form, there's 20 different amino acids, and they form all the proteins in your body. What do you think the functional groups are on an amino acid?
Amines.
One would be an amine. So 1 part of the amino acid is an amine. What about the acid part? What would be the functional group of the acid part?
Carboxylic acid.
Carboxylic acid, exactly right. So this is the amine part of an amino acid, and the other part is the carboxylic acid part. And it's these 2 that come together and form amide bonds. And so your body has trillions of these amide bonds, and that's the main bond keeping proteins together. It's the amide bond. And so amide bonds are pretty strong because you don't want your proteins, obviously, to just fall apart. But you also don't want that bond to be so strong that you can't break it when you want to. And so that's what these amide bonds do for us. They're stronger than ester bonds, but they're not so strong that you can't break them when you need to. And so there are enzymes that break these amide bonds. There's lots and lots of enzymes that do that when you need to cleave up proteins all through the protein or in very specific places. So let's have a look at some of these. So this is diphenhydramine. That's, so if anyone's ever taken Benadryl, you know, when you got hay fever or whatever else. I took Benadryl for my SATs. Actually, it kind of helped, I think. What are the active ingredients? The active ingredient. What are the functional groups present in A?
Is one the benzene?
One is not the benzene, because benzene, oops, let me go back. Benzene is not reactive. Benzenes are particularly non-reactive. So that is not a functional group.
Is it nitrogen with the oxygen? With the
The nitrogen is not attached to the oxygen. So the
Or-
nitrogen is a functional group. What would we call that?
Mean.
An amine, that's right. Would it be a primary, a secondary, or a tertiary amine?
Tertiary.
Primary.
Tertiary, that's right. Excellent, because there's 3 carbons attached to it. So there's one other functional group here. What is it?
oxygen?
The oxygen. So what's the functional group there?
It's an ether.
That's an ether. Excellent. That's right. So diphenhydramine is actually an ether. So Novocaine, anyone working in a hospital or in a dentist's office certainly is familiar with Novocaine. Where are our functional groups there?
Is there a ketone?
No. It's not actually, if this second oxygen wasn't present, it would be a ketone. What do we call this whole thing? Just mentioned it a minute ago. Starts with an E.
Is that the ester?
That's an ester. That's right. Because we have the carbonyl group attached to an oxygen. So that's basically, that means that that was a carboxylic acid at one time. But then we replaced that oxygen with the rest of this group here. So some synthetic chemist or something had a carboxylic acid and then added this, probably had an alcohol group at the end there and then put them together.
So for that one in particular, so that one you said is a it would have been a carboxylic acid.
Yeah, basically, yeah, this is the remnants of a carboxylic acid. When you have this, basically that used to be a carboxylic acid at one point, and now it's become an ester. So where are other functional groups? There's 2 more.
There's the amine at the end part.
There's 2 different amines. Which one are we?
The NH2.
NH2, that is an amine, that is correct. Is it a primary, secondary, or tertiary?
Primary.
That's a primary, that's right. It's only attached to one other carbon. And what about this one here? Primary, secondary, or tertiary?
Tertiary.
That's tertiary. Excellent. Great job. Okay.
Can you go back to that, or did you already erased it?
Oh, I think I can put it back. What were you looking for?
Because I don't see that example in our notes. I usually take a picture and then draw it.
Oh, yeah, I think I used the wrong set of slides for the, I can include these.
Drawing it helps because then it makes it easier to understand.
Okay.
Thank you.
Okay. So we'll start at the beginning with alcohols. So alcohols are really simple molecule because basically all they have is just the OH group, the hydroxyl group. That's it. If it has that group in it, it's an alcohol. And so they're similar in structure to water because of the way that oxygen bends its two bonds. Remember, it has these two lone pairs, a hydrogen, and then a bond with something else. So if that other bond is with hydrogen, we know that makes water, and water is bent. If that other group is R, whatever it happens to be, it has the same bond angle as water. So it's still around about 109.5 degrees, just like water. So we give it the ending all, and then name the parent molecule with however many consecutive carbons, just like we did with alkenes and alkynes and alkanes. And if it's a substituent, then we just call that group a hydroxyl. So that, like I said, that's not, we call that in chemistry a hydroxyl group. So there's an interesting thing, interesting thing about alcohols is that just like water, because they are functionally similar to water, they have the same shape at the end, they can hydrogen bond just like water can, because they've got the hydrogen bonded to an oxygen, which you need for hydrogen bonding. So they've got hydrogen bond donor here, and that they've got hydrogen bond acceptor there. So alcohols hydrogen bond with each other. And because of that, they have a much higher boiling point than other organic compounds that are similar. And the real obvious example is look at methane. Methane has a boiling point of like minus 164 degrees. So methane is a gas until you get to really, really, really cold temperatures. All you need to do is pull one of those hydrogens off and replace it with a hydroxyl group, and you've got methanol. And look at the boiling point of methanol. It's like 230 degrees higher. So just the presence of that one hydroxyl group increases the boiling point by 230 degrees. So that is a huge difference. So it also tells you how strong hydrogen bonding is. And then as the length of the nonpolar group increases, our R group with all the carbons on it, as that gets longer and longer and longer, then you start to see the additional London dispersion force take over. And so methanol boils at 65, ethanol boils at 78, propanol boils at 97. And then the more and more carbons you add, the higher and higher the boiling point goes. So the big jump is because of the hydrogen bonding, and then the smaller increases are because of the London dispersion forces. So here's some of the real common ones that we use all the time. So methane becomes methanol, ethane becomes ethanol. And then remember, when we start getting longer carbon chains, you have to say where the hydroxyl group is. Once you get 3, it's either going to be on the end or in the middle. So you have to say it's either 1 propanol or 2 propanol. And then with butanol, with 4, you would either be at 1 or at 2, the same. These would be then secondary alcohols when the hydroxyl group is on the inside of the molecule and not at the end. And so when we have 3 carbons attached to the carbon that contains the hydroxyl group, that is a tertiary alcohol. So this one, we have the carbon with 1, 2, 3 methyl groups attached to it and the hydroxyl group. So unlike amines, it's not the oxygen attached that makes it a primary, secondary, or tertiary. It's the carbon that's attached to the hydroxyl group that makes it a primary, secondary, or tertiary. So primary would have just 1 carbon attached, secondary would have 2 carbons, and then a tertiary would have 3 carbons. And then remember, when we have a ring, we just have that 1 functional group. We don't have to say where it is because that is assumed that's carbon 1. So we would just call that cyclohexanol. It's got 6 carbons, it's got a hydroxyl group on it. That's carbon 1. Don't have to say anything else, just cyclohexanol. So let's look at some of the reactions that these alcohols are involved in. Now there's a couple that produce alcohols, and we call those reductions. Reductions basically meaning it reduces the amount that carbon is bound to oxygen. And the most common one is when we have carbon monoxide. If you treat carbon monoxide and hydrogen in the very high temperature and high pressure, you reduce this bond to oxygen and this bond to oxygen and replace them with hydrogens. And so you're left with 1, 2, 3 hydrogens and a single hydroxyl. So basically we've added 3 hydrogens to the carbon and 1 hydrogen to the oxygen. So we call that a reduction because we're reducing the amount of bonds that carbon is making with oxygen. It was making 3 bonds before, and now it's only making 1. So we call it a reduction. The other reduction that can take place under similar circumstances is with ketones. So if we have a ketone here, that carbon is making 2 bonds with the oxygen. So the same thing takes place. We pump in high concentrations of hydrogen at high pressure and temperature, and the hydrogen takes one of those bonds away from the oxygen and one from carbon and replaces them with hydrogens. So now we have a hydrogen here and a hydrogen attached to the oxygen. And so we call those reductions. So that is one. So either a triple bond can be reduced or a double bond can be reduced. We can't reduce single bonds. Reducing single bonds would mean you would break them. But double bonds and triple bonds we can. And one of the reactions you know about already. And that's the hydration of an alkene. That's the Markovnikov reaction. So this one, instead of pumping in hydrogen, we're using water and a very strong acid catalyst. And so we're adding a hydrogen there and a hydroxyl there, using the Markovnikov rules of the hydroxyl goes to the carbon with more carbons attached to it. Hydrogen joins the carbon with more hydrogens attached to it. So that one we already know. Now we could also oxidize alcohols. Now, what does oxidation mean? Oxidation basically means instead of reducing the number of bonds with oxygen, we're increasing the number of bonds with oxygen. So we're pulling more and more electrons away from carbon. We're oxidizing it by increasing either the number of oxygens it's bound to, or we're increasing the number of bonds with oxygen. So here we've got a primary alcohol. Oops, let me go back. So here we've got a primary alcohol. So it's got a hydroxyl at the terminal end. This one, what alcohol would this one be?
Is that isopropyl?
No. It's all in a line.
Butanol?
Yes, butanol, right? Is it? Yeah, butane is 4. I tell you, I'll be teaching this class for 50 years and I will not be able to get propanol and butanol together. But yeah, 4 is butanol. So we oxidize that and basically we remove the hydrogen and we increase the bonding with that oxygen. And so we turn the alcohol into an aldehyde. That is an oxidation because now that carbon is doubly bonded to the oxygen rather than singly bonded. And then we can oxidize that even further by doing another oxidation reaction, and we add even more oxygens to that carbon by turning it into a carboxylic acid. So now it has a double bonded oxygen and a single bonded oxygen. So now that carbon barely has any of its electron density at all. It's being pulled by this double bonded oxygen and this single bonded oxygen. That's with a primary alcohol. When we have oh, go ahead.
So in these reactions, it's always just a double bond?
What do you mean?
Like, because you said that it with the increase of oxygen, it creates a double bond with oxygen. Is it always just a
Yeah,
double?
so there's two basic oxidation reactions. One, you just attach more oxygens, or you increase the bonding with the same oxygen. So the first reaction is increasing the bonding with the same. So that's the same oxygen as was there before. Now it's just more bonded. So that's the first reaction. And then the second one is adding a second oxygen. So we go from alcohol first to aldehyde and then to carboxylic acid. We can't just jump right to carboxylic acid. We need to get rid of that hydrogen first. So now we have a double, and then we add another oxygen. And since carbon can only make 4 bonds, that's it. We can't add anything else. So it's making 4 bonds. It's making 2 with that oxygen and 1 with that one, plus the 1 bond with the carbon next to it. So it can't make any more bonds.
Thank you.
And I'm glad you mentioned it, because that's a perfect segue, all hail Queen segue, to the second part when we're dealing with secondary alcohols. Now, when we have secondary alcohols, that means the carbon that's attached to the hydroxyl group is already attached to 2 other carbons, right? So when we oxidize that, we do the same reaction as we did before. We remove that hydrogen and make a double bond with that oxygen. but then we're done. And the reason is that carbon's already making 4 bonds now. We can't make any more. So we can't remove any more hydrogens and replace them with oxygens. There aren't any more hydrogens, so we're done. So then there's no reaction after that. So we can oxidize a secondary alcohol to a ketone, and then we're done. We can't go any further because it's already making 4 bonds with carbons and oxygens, and we can't replace anymore. Hydrogens we can pull off relatively easily. Carbons removal is much more difficult. It's a much more active reaction. So if we have a tertiary alcohol, this carbon is already making 4 bonds, 3 with carbons, 1 with that hydrogen, or 1 with that oxygen. So we can't even do anything to that. So we can't form a double bond with oxygen, because then that would be 5 bonds, and carbon can't do that. So basically there's no hydrogen there to oxidize. There's nothing, we can't remove a hydrogen and replace it with an oxygen. So we're done. So basically a tertiary alcohol is, we can't oxidize those. We can do reactions to the oxygen, but we can't do any reactions to the carbon. Now, everyone's probably familiar with this particular reaction if you've had a rough weekend. So there's an enzyme in your body that actually does that reaction. Now, this enzyme is called alcohol dehydrogenase. What do you think a dehydrogenase does?
Dehydrates you.
It dehydrates, it removes hydrogens. And so it pulls off hydrogens from molecules and creates water, right? It dehydrates. So it pulls off this hydrogen from ethanol and gives you that double bond. So now you have a double bond. That makes ethanal. And ethanal is nasty stuff. That's an aldehyde. And that's where you get the super bad hangover and your head is pounding. Ethanal is very chemically reactive. And so it's doing a lot of reactions your body really doesn't like it to be doing. And so eventually you clear out all the ethanol because the enzyme keeps going. It keeps breaking down the ethanol and oxidizing it and turns ethanol into ethanoic acid. It turns this into this, and that's acetic acid. And that's kind of nasty for your body to have too, but it's not nearly as reactive as ethanol is. So you can just clear that out. So you don't want ethanol around because basically what aldehydes do is that they just cross-link themselves. They just react with basically anything. And so that's one of the reasons why everyone's heard of formaldehyde, right? You've probably heard of formaldehyde. And why it's a good preservative. Why it's a good preservative is basically it reacts with anything with carbon in it and links them together. So it prevents things from falling apart by sticking them all together. Well, your body doesn't want all of its molecules to be stuck together. Better for when you're dead, I suppose. Okay. Now, with alcohols, you can go back to making the alkene. So it's exactly the opposite reaction of hydration, where you take an alkene, you add water to it. Going backwards, you still have the same very strong acid, but now you use a lot of heat, and you're just in the presence of just the strong acid. And that goes backwards. That is actually removing the hydroxyl group, turning that into water, So it removes, be able to draw in here. Removes this hydroxyl and this hydrogen as water. So it dehydrates and reforms that double bond. So that is also another reaction that alcohols can do, the opposite of the Markovnikov reaction. And the same rules apply. All right, so here's a couple of alcohols. What is the first one?
Butanol?
Yeah, it's got 1, 2, 3, 4 carbons. So yeah, butanol. And so we would call it either 1-butanol, or another name is N-butanol, meaning that it's just a long chain and the alcohol's on one end. What would we call this one?
Is that a tertiary propanol?
It is. So have to see how it is a tertiary alcohol. So how many carbons? We've got 1, 2, 3, 4.
So that's a butanol also then. 'Cause you said
What's
4.
the longest chain though? What's the longest continuous chain you can make?
Propane.
3, right? Exactly. So 1, 2, 3. So what will we call that then?
A 2-methyl.
Yep.
2
We're almost there.
Propanol.
Propanol, excellent. Then here we've got, so C, we've got a ring. Now, is that an alkane? Or is it benzene? Is it an aromatic ring?
I thought benzenes had to have the double bond as well. You know, the alternating double bonds.
So what is it? Is it an alkane or is it an aromatic?
Believe it's alkane.
It is. Excellent. It's an alkane, right? So what will we call that? So it's got how many carbons in the ring?
6.
6, right? So it's a hex.
So it'd be dimethyl hexanol.
Yep. But we need more information. Yeah, so there's your dimethyl group. So it is dimethyl hexanol, but we need more information because we need to say where the dimethyl groups are in relation to the alcohol group. So what do we call it?
2,2-dimethyl.
Yeah. Excellent. 2,2. Yeah, because they're both, that would be position 1 because that's where our alcohol group is, and then the 2 methyl groups.
Professor, I have
Yeah.
a question.
Yep.
What if there's a double bond inside the ring?
Oh, great question. Then I think the double bond would get priority. And so we would start naming them relative to the double bond. So let me draw one. So for instance, if we had a double bond there, then we would name these in order to get the lowest numbers we can. So that would be 1, 2, 3, 4, 5. No, 1, 2, 3, 4. I guess it doesn't really matter which way we go. So that would be 4-hydroxy 2,2-dimethyl cyclohexene. Yeah, great question.
Why is it 2-2? Like, do you number first? Would you number first the OH and then you number the two dimethyls, or?
Well, you have to mention that there's dimethyl just means there's 2 methyl groups somewhere on the ring. If they're both on the same carbon, then you have to say 2,2 to make
Oh, I
sure that
see.
you say we have 2 methyl groups, but they're both the same place. Or else
I
it'd be like
see.
2,3 or 2,4 or 2,5, depending where they are.
Because
so
the-
we always
oh.
do 2,2 if they're in the same place.
Okay,
Yeah.
because I was thinking the OH, so does OH come, does it take priority over the methyl groups?
Yes.
Okay.
Yeah.
And then, I'm sorry, for B, I'm trying to understand, how you got 3.
Oh, that's the longest stretch, longest
just kind of-
continuous stretch of carbons.
It's just kind of weirdly
1,
shaped, so I'm just trying to
2,
read it.
3.
Oh,
Could
I
also
see.
go 1, 2, 3, and we get the same. Basically, you just be named the same thing.
Okay,
Yeah, we can't say 4 because we can't get 4 of them in a row. We can
Okay.
only get 3 of them in a row.
and I'm sorry, what was the name for this one again?
2-methyl 2-propanol.
Okay,
Pro because it's 3.
okay.
Ooh, I got that right that time. Not screwing it up. So ethers. So as I mentioned, ethers don't have any other groups bonded to the oxygen except carbons. So it has a carbon group on one side, carbon group on the other side. So it can't hydrogen bond because there's no hydrogen attached to the oxygen. They do have a dipole because we got oxygen, and this is going to be bent, right? Because when oxygen has 2 single bonds and it's 2 lone pairs, this is always going to be bent at around 109 degrees. Depending what the groups are, they're big bulky groups that may change the angle somewhat. But if they're just sort of long alkanes, it's going to be around 109 degrees. That means you're always going to have a dipole there. So it does have dipole-dipole interactions, but since it can't hydrogen bond, you're not going to see that big increase in boiling point. For instance, propane boils at -42. We pop out that methylene group. Methylene is the CH2 group in the middle. Take that out, replace it with oxygen. It does increase, but not as dramatically as when we make a hydroxyl group. When we increase the size of the carbon groups on either side, that starts to increase the boiling point based on London dispersion force. So this is the ether that most people are familiar with, like that was originally used for knocking people out as an anesthetic back in the very first days of anesthesia. Although it's pretty nasty stuff. Basically, it works because it looks like alcohols. So, it's not a great idea to sort of knock yourself out with alcohol either, because you don't feel great when you wake up. But that's how ethers work really, really fast, because they have very high vapor pressure. So you get a very high gas concentration. And so it gets to your brain really, really quickly. So then naming these. Basically, you just name the groups attached to the oxygen atom, and then with ether at the end. So you generally name the longer chain first. So if I had butyl methyl ether, that means I would have a butyl group on one side with 4 carbons and a methyl group with 1 carbon on the opposite side. So butyl methyl ether. What would we call this one? If we have the same group on both sides, we just call it di. So what do we call that one?
Diethyl?
Diethyl ether, right? You just call that diethyl ether because we've got 2 carbons on either side. What about this one? This one's tricky. This one's a very special group. We haven't really talked about it much. How many carbons in this group here?
Is it 3?
It's actually 4. 1, 2, 3, 4. So it's got 4 carbons. And the way that's broken down is has a very specific name. So it's propyl because it's propane 4, but I'm sorry, no,
Or is that a butyl?
butyl. No, but it's this particular group, the way it's has a carbon here, carbon there, carbon there. This particular group is called isopropyl. So we call this isopropyl methyl ether.
So is it a butyl, but it's called something different?
But it's called isopropyl, yeah,
Okay. But
because it's got those 3 carbons, but all attached to the same one. So it's called an isopropyl group.
the general makeup of it though makes it considered a butyl.
Yes.
Because of the 4.
Mhm. Now, there is another method of naming this. And that is by using calling this whole thing a substituent. So if this was a hydrogen, we would just call it a hydroxyl group. But if it has a carbon attached to it, so if this is CH3, we call it methoxy because it has a methane, single carbon, and an oxygen. And so here we would just call this 1, 2, 3 methyl. So that would be 2 methoxy, 2 methyl propane. So 1, 2, 3 carbons with a methyl group and this methoxy group. Now, if it was in 2 carbons attached to the oxygen, we would call that ethoxy. And that's generally where we would end that, because if they get any longer, then we just refer to them as ethers. But sometimes when we have like really short carbon groups attached to the oxygen, we sometimes use the methoxy or the ethoxy, but generally stick with just calling them ethers. All right, so aldehydes, ketones. I'll try and move this along a little faster. Now here are 2 groups with our carbonyl. And as I've mentioned, the carbonyl is really important because since we have 4 electrons bound to that shared between the carbon and the oxygen, we have a bigger increase in the partial positive and a bigger increase in the partial negative charge. And so it's a lot more polar than ethers. This is a very polar molecule. So if we have an aldehyde, we see a big increase in the boiling point. And that's not because of hydrogen bonding, because aldehydes don't hydrogen bond, but it's a really strong dipole. So they don't hydrogen bond because the hydrogen isn't attached to the oxygen, it's attached to the carbon. So it can't hydrogen bond, but it does have a really strong dipole. So you have a really strong dipole interaction that increases the boiling point. When you add hydrogen bonding, the boiling point goes up even further. So that makes a much bigger difference than just a smaller dipole that ether has, when you have a much stronger one because of the double bond. Now, naming these things, don't be terrified of all the, you can read it a little later. It's a little more straightforward. Again, just find the longest straight chain carbon you can, and that's the parent alkane, butane, propane, whatever it is. Find the longest one. If it's an aldehyde, that's going to be at the end automatically, and you just add the name al. So that one's pretty straightforward. For a ketone, you add the ending -one, but you have to say which carbon it's on, because aldehyde is always at the end, so we don't have to name it. It's always at one end or the other. Ketone, that carbonyl group could be anywhere except the end, because if it was at the end, it would be an aldehyde. But because it's somewhere in the middle, you have to say where it is. So to indicate it, number it in the manner that gives the carbonyl carbon the lowest possible number. Now remember, if it's in a circle, if it's a cyclic molecule, you just automatically assume whatever one has the carbonyl group, has the double bonded oxygen, that's carbon 1. So let's look for some examples. So here we have methane turned into methane al. And the other common, that's the common name for that one, is formaldehyde. So that's what we talk about, formaldehyde. That's what we're talking about. Ethane becomes ethanal, propane, propanal, and so on. So aldehyde's pretty simple. Ketones are a little trickier because you just have to name where it is. So these are some of the common ones. So propanone, 3 carbons, don't have to say where the carbonyl group is, because it has to be in the middle. can't be at either end because then it would be an aldehyde. Once we start moving it around, then you give it the name 2-butanone, 3-pentanone, because it has 5 carbons in it. The common names for these, what they used to be called, it's just basically they would be named by whatever groups were on opposite sides of the carbon. So here I've got a methyl group, here I've got an ethyl group. So it used to be called ethyl methyl ketone, but the proper scientific name is 2-butanone. So because this is a circular alkane, and it just has the single carbon oxygen double bond on it, that's just automatically referred to as 1. Okay, so just find the longest chain and then use the smallest number you can to give it the location. So here we would not call it 5-hexanone going from this side to the other side. We go backwards and name it 2-hexanone. All right, keeping you guys here forever tonight. So these, I'm going to end with the mercaptans. These are, like I said, these are nasty molecules. They smell really, really bad. So hydrogen sulfide, we've sort of learned about hydrogen sulfide before. That isn't an organic molecule. Why isn't it an organic molecule?
No carbon.
There ain't no carbons there. Can't be organic. That's right. So that's the smell with like rotten eggs. And that is actually added to natural gas. So if you have a natural gas leak in your house, you can smell it, because if the hydrogen sulfide wasn't there, you could be having a gas leak and you'd never know it, because methane, propane, they don't smell like anything. And so you wouldn't know, and you basically, your house would blow up, or you would just suffocate and not know it. So it's added to it to let you know there's something bad. Everyone smelled skunks on either in your house or on your dog or on the highway. And that has the mercaptan at the end here. And interestingly, if you've had a skunky beer, I haven't had one in quite a while, but if you have a skunky beer, it's exactly the same molecule as skunks make, except that there's a double bond there. So very, very same molecule, with just one very small difference. But since they both have thiol group or mercaptan group at the end, nasty. So we name them sort of just like we do alcohols. So alcohols, since they're so similar, we just put all at the end. But with sulfur, we put thiol at the end. It's a hydroxy group. It's a mercapto group. If it's in the middle, it's an ether. And with sulfur, we call it a sulfide. So we think of sulfide as being that. An organic sulfide has sulfur with 2 carbon groups attached to it. And so some of the key reactions are this one is probably the most important: oxidation. And when sulfides, or when these thiol groups oxidize, they form disulfides. They have these disulfur bonds. And that is another reaction that keeps proteins together. There is an amino acid called cysteine that has a mercaptan at the end. And one of the uses for cysteine in proteins is to cross-link with another cysteine, oxidize, and form this disulfide bridge. So what that does is it takes like floppy parts of proteins and basically locks them in place. And it's a very easy reaction to reverse. So you can reduce this very simply. So what I wanted to point out was that if you look at some of these, some of the amino acids, all the functional groups I've been talking about are present in amino acids because they're the ones that are going to be doing all the biological reactions inside of enzymes and proteins in your body. So we can see that we've got carboxyl groups, aspartic acid, glutamic acid, both have carboxyl groups at the end. We have positive charge. Here we have an aromatic amine. Here we have a primary amine. Here we have secondary amines. We also have polar side chains. We have a hydroxyl group, serine, primary alcohol. Here we have a secondary alcohol on threonine. Here we have an amide bond on asparagine and on glutamine. And then cysteine has the mercaptan group, which is able to make those sulfur-sulfur disulfide bonds. Okay, so that went a lot later than I really wanted to. But you guys have questions about any of these before I give you a little break?
Is that slide, is that something you can send us?
I will include, yeah, I will include it. I realized I submitted the wrong set of slides and then posted them. So I'll fix that. I'll replace it with the right.
Or can I just screenshot it then?
Sure.
Thank you.
You're doing that? Okay.
Yeah, I just did it. Thank you.
All right. Yeah, I'll also post it. Because this wasn't in the original set of slides. Then as I was reviewing the chapter, I realized one of the things that was sort of left out, I thought, which was really important, was that since we're going to be talking about more biological organic chemistry at the end of the term, I really wanted to show why these functional groups are so important and where in chemistry and in biochemistry in particular, we use them. And it's because of the side chains of amino acids. And basically one of the only things that side chains can't do is have a very high permanent positive charge. Lysine here, oops. Where are we? So lysine here is positive under most pH conditions, but not all pH conditions. And so that's where things like vitamins and cofactors come in. Vitamins and cofactors provide enzymes with the functional groups that amino acids don't have. So that's why they're so important to have in your diet. But we will get to that a little bit later. So I have posted the worksheet in the chat and also posted it to Canvas. So why don't we get back together again at 8:30 and get started on that, okay?